Hello, AP Stats students. Welcome to session 7 of AP Daily Live Review. I'm Darren Starnes, coming to you from beautiful Hilton Head, South Carolina. I've been a longtime AP Statistics teacher and AP exam reader. Thank you for joining me. I've got a lot to share with you in this session, so let's get to it. As you can see, session 7 is about tackling the AP Statistics investigative task. As always, there'll be some materials that you'll want to have in front of you for the session, and these are hosted at this tiny URL address. If you haven't already downloaded the handout, this would be a good time to do so. So I'll leave that tiny URL for you on the screen. So the handout for this session we'll be using, along with the formula sheet and the inference flowchart that we discussed back in session 5. As we go into the folder, we'll see this big long list of things. I'm going to go there now just to show you something about the handout for session 7. I tried to once again make it as easy as possible for you. So if you do scroll down and take a look at that handout, what you'll see is the questions that we're going to address during this session. Question 1 takes up 2 pages. And then question 2 is going to take up the remainder of the handout. But at the top of question 2, you'll see hyperlinks to the inference flowchart and the formula sheet. So if you want to hold off on downloading those 2, if you don't already have them, we can go ahead and get started, and you can just click off of the handout. The other thing that would be helpful for you to have in front of you is your graphing calculator. I'm going to be using a TI-84 during the session. So with that, hopefully handout's ready. If you need another second or 2, just pause the video and grab that handout. So what will you learn in this session? As always, our goal is in every session are first and foremost to help you review the essential content and skills of the course that you're likely to need on the AP exam. Second, especially with this session, to help share some specific strategies for success tackling the AP Statistics investigative task. And most importantly, to build your confidence and help maximize your exam score. So our plan for this session, we're going to start with some quick facts and a couple of suggested strategies for the investigative task. In other sessions, I've sort of shared the strategies as we went along, but I want to present them to you up front with a little commentary, and then you can see how we use them as we get to that particular issue in a question. We'll be working through 2 investigative tasks from previous AP statistics exams, just to give you the flavor for what these might look like. A few quick facts. So the investigative task is going to assess you on multiple skill categories and multiple content areas, focusing on the application of skills and content in new contexts or in non-routine ways. That means you will have never seen a question exactly like the investigative task before. Even if you've been preparing for this task of the investigative task in your course, you will never have seen a question exactly like the one that will be presented to you. So you have to be ready to think outside the box. You should expect this question to span multiple units of the course. That's almost a guarantee. And the other big thing about this question, the big fact, is how long it is in terms of time. You have about 25 minutes dedicated for this one question. That's the last question on the free response section. And look how much it counts, 25% of the free response section score. That's 12.5% of the entire exam score. So one comment before we even get to strategies is you don't want to score a 0 on this question, either because you didn't get to it or you weren't able to make any progress on it. And we're going to try to make sure in this video that those things don't happen to you. Let's talk strategies, previewing what we're going to be using in the session. First, on any of these outside the box questions, you want to start with what you know. The question writers will build some things into the early parts of the question in particular that are things you're familiar with to try to draw you into the question. The question writers want to see what you can do when you have to apply your concepts and skills in an unfamiliar way. So if you start with what you know, you might at least be able to earn some credit on the question and avoid earning a 0. Next, you've got to be prepared for some unexpected twist. The question writers are trying to take you outside the content you've studied and the skills that you've used in particular ways throughout the year. So you know at some point a twist is coming. Just be on the lookout and embrace it. This is really key. There are going to be multiple parts to the investigative task, perhaps as many as 4. If you get stuck on one part, and it's a part that has some kind of answer that's numerical, or an answer that's a yes/no choice, go ahead and make up an answer, even if you don't feel very confident about it, and use that answer in subsequent parts. Next, in many of the investigative tasks, there'll be one or more of the parts toward the end of the question that require you to summarize your understanding of what's happened to that point. So be ready for that. You'll have to think back through several earlier parts and distill what you've learned from them. And the big strategy for success on the free response section is to manage your time wisely. There are some students who found that of the first 5 free response questions, let's say there are 3 or possibly 4 of them that they feel pretty confident about. They'll do those 3 or 4 first, and then the 1 or 2 that they aren't feeling so confident about, they'll hold off and get started on the investigative task. Read the question, do the first part or 2, kind of get into it. If it's going well, they'll keep going. If it's starting to run into some roadblocks, they'll stop work on the investigative task and go back to the 1 or 2 free response questions that they skipped earlier. And then they'll return to the investigative task at the end. Sometimes walking away from a problem is the best way to help you solve it, because when you come back, you can take a fresher look at it. Those are the only 5 strategies that we're going to talk about, but I hope you'll see how they get used as we get into these 2 example questions. So let's practice. Our first investigative task came from the 2021 exam, and it's about baseball. It says attendance at games for a certain baseball team is being investigated by the team owner. The following box plots summarize the attendance measured as average number of attendees per game for 47 years of the team's existence. The box plots include the 30 years of games played in the old stadium and the 17 years played in the new stadium. Part A of the question says, compare the distributions of average attendance between the old and new stadiums. You can see the box plots here. We have old stadium and new stadium, and then average attendance in thousands. Always good to read the labels on the axes. So remember my first strategy, start with what you know. This part A could be an entire question earlier in the free response section to compare distributions of quantitative data. You know what to do. We've talked about it in an earlier session. When you compare distributions of quantitative data, there are 5 elements that you should include in your response. And you know what they are: shape, unusual features, center, variability, and of course, context. We'll start with shape. The distribution of average attendance in the old stadium appears roughly symmetric, while the distribution of average attendance in the new stadium appears skewed to the left. Next, having covered the shape and a little bit of context there because we talked about average attendance, we'll move to the unusual features. Neither of those distributions has any outliers. If they did, we would see some sort of asterisk or other symbol on the box plots past the whiskers. So we've covered unusual features. Next, we talk about center. The average attendance was higher for games played at the new stadium, median about 25,000, I would say, than for games played at the old stadium, the median's about 16,000. So we've given some evidence from the graph that indicates why we think the average attendance was higher for games at the new stadium. And lastly, we'll talk about variability. It looks like there was slightly more variability in average attendance at the new stadium, whether you measure the interquartile range or the range, that is the maximum minus the minimum. So slightly more variability because of both the range and the interquartile range being larger. So we've covered all of the 5 components. Now I'll just make one comment about using box plots to describe shape. A box plot can hide a lot of aspects of a distribution, including how many peaks it has. We don't know if it has one clear peak or multiple peaks. We don't know if there are any clusters of values in the distribution. We don't know if there are any gaps. So a box plot gives a very incomplete description of shape, but it does help you think about the basic shape, looking at the upper half of the distribution from the median to the maximum versus the lower half of the distribution from the median to the minimum for each of the 2 graphs. And that's why I commented that the distribution for the new stadium appears to be left skewed, because the lower half of the distribution is a lot more spread out than the upper half. But that's about all we can say in terms of shape. All right, you can do part A. Unfortunately, it's only part A, so we've got to keep rolling. Part B, the following scatter plot shows average attendance versus year. Compare the trends in average attendance over time between the old and new stadium. So you have to be sure you understand what the question is asking you to do. We want to compare the trends between the old and the new stadium. All right, let's do it. Let's start with the new stadium, the one with the solid black dots. During the years in the new stadium, the average per game attendance increases somewhat linearly from about 16,000 people in 2000 to about 27,000 people in 2016. However, during the years in the old stadium, it looks roughly constant. There's no obvious increasing or decreasing trend over time for the average per game attendance. The average attendance tends to, or appears to, vary about an average of approximately 16,000 attendees. So it varies around that kind of central value from 1970 through to 1999. So I'm kind of picturing with my hand, it looks like the trend is flat, whereas for the other one, the trend is obviously upwards. All right, let's go to part C. So parts A and B are both things that you should feel pretty comfortable doing. We're going to start to move into new territory soon. So C says, consider the following scatter plots. Part 1 of C. Graph 1 shows the average attendance versus number of games won for each year. Describe the relationship between the variables. So now this is a task you've done a lot in your course, describing the relationship between 2 quantitative variables shown in a scatter plot. You know how to do that. There are certain things you should include in your response every time. So we'll focus on graph 1, and we'll be sure to do those things: the direction, the form, the strength, any unusual features, and of course, context. So graph 1 shows and I'm going to try to do them in some order here: positive, linear, strong. The points fit fairly close to a linear pattern. And then relationship between number of games won and average attendance. I want to be sure I got the context in there. So the thing I'm missing so far is unusual features. I'm going to look at the graph and see if anything stands out at me particularly. There are no obvious outliers in the graph. That would be one comment. All the points seem to be along the same basic straight line pattern. So I want to go a little deeper on 2 of these descriptors now that I've done the 5 required elements. In several past AP exam questions, students have been asked to talk in more detail about what linear means. So linear has to do with a constant rate of change, or approximately constant rate of change. So in this case, the average attendance increases at a fairly constant rate of about 500 attendees per game for each additional game won. So at some point, you might be asked to explain what you mean by a linear relationship. Likewise, what do you mean by a strong relationship? Well, you mean that the variation about whatever kind of form you're seeing, in this case, the linear form, is fairly small. And as we look at it, it's also the case that the variation around the line is pretty similar at all x values. So those are two tasks you might be asked to do another time. Those were not required for full credit here, but many students did go on and talk about the linear aspect of the graph or the strong aspect of the relationship. Let's go to C2. Now we're going to focus on graph 2, which shows the same information as graph 1, but also indicates the old and new stadiums. So same points, but different symbols for old and new. Does graph 2 suggest that the rate at which attendance changes as number of games won increases is different in the new stadium compared to the old stadium? Explain your reasoning. And I've underlined that as part of my active reading because I want to be sure that we don't just choose an answer, yes or no, and not justify it with evidence from the graph. So let's take a look here at graph 2. We're focused on the rate at which attendance changes as number of games won increases for each of the two stadiums. All right. Well, I think my answer is no. It looks like the average rate of increase is about the same throughout the graph. So here's a possible response: no. I've answered the question. Graph 2 suggests that the rate at which average per game attendance increases as the number of games won increases are about the same for the two stadiums. A line drawn through the points for the old stadium, and I'll sketch one on there, has about the same slope as a line drawn through the points for the new stadium. And I might on the exam actually just sketch the line and convince myself that no is the answer I want to back up with my justification. All right, that brings us to D. I told you there was going to be potentially 4 parts, and here they are. It says, consider the 3 variables: number of games won, year, and stadium. Based on the graphs, explain how one of those variables could be a confounding variable in the relationship between average attendance and the other variables. A confounding variable. All right, let's just recap. There was the set of box plots we described in part A. And then we started focusing on the scatter plots as we wanted to look at the relationship between number of games won and average attendance. So we'll need to keep those graphs in mind as we compose a response because it says based on the graphs. This is the unexpected twist in the problem. You may have been asked about confounding in your course before in the context of a study design, but you probably haven't been asked about confounding in a scenario where you were given lots of graphical evidence like this. So let's take a look at a possible solution. The number of games won could be a confounding variable for assessing the potential effect of opening the new stadium on average per game attendance. The box plots in part A show that average per game attendance tended to be higher for games in the new stadium than for games in the old stadium. But the cause of the increase may actually be that attendees were more excited about attending games for teams that were better at winning. Kind of makes sense. The scatter plots in part C show that average per game attendance has a strong positive correlation with games won, and the team tended to win more games playing in the new stadium than in the old stadium. So let me break down that solution in terms of the scoring guidelines for this more investigative aspect of the problem, discussing confounding based on graphical evidence. So the scoring guidelines provided had several pieces. First, the response had to state that there is an association between attendance and one of the explanatory variables, either stadium or year or wins. And that was done here. Average per game attendance tended to be higher for games in the new stadium than for games in the old stadium. That's using the box plots. So we have an association between stadium and attendance. Next, the response has to state an association between attendance and a different explanatory variable that might help explain the attendance. So it says the scatter plots in part C show that average per game attendance has a strong positive correlation with games won. So we have a connection now between attendance and number of games won, wins. So that's 2 different explanatory variables, both related to the response variable of per game attendance. And then third, we need to state that there's an association between the 2 explanatory variables themselves, the ones that we identified in components 1 and 2. So that comes in the final sentence here. The team tended to win more games playing in the new stadium than in the old stadium. So we have a connection between the wins and the year, I'm sorry, wins and stadium. All right. And then finally, for confounding, we need to explain that the variable we identified as the potential confounding variable could be the cause of the association between attendance and the other explanatory variable we identified. So the cause of the increase in attendance may actually be the attendees were more excited about attending games for teams that were better at winning, and not just because of the new stadium. So it's that relationship is confounded by this other variable. Whew, we've done one. That was a lot. We're going to move on to our second investigative task that's going to take us into the inferential part of the course. This one says, a drug company currently sells a prescription pain reliever that has been shown to be effective at lowering arthritis pain. However, since the drug also causes stomach irritation in some patients, the company has created a new formulation that it hopes will reduce that side effect. To see if the new formulation reduces the occurrence of stomach irritation for users of the pain reliever, the company conducted a small preliminary study to compare the new formulation with the current pain reliever. In the preliminary study of 100 subjects with arthritis, 50 were randomly assigned to take the current pain reliever, and 50 were randomly assigned to take the new formulation. Patient responses at the end of the study are summarized in the table below. And you can see the current pain reliever versus the new formulation and whether the patient had stomach irritation. You see the 50 per group and the overall 100 total subjects. Part A of the question asks, do the data from the preliminary study indicate at the 10% level of significance, that seems important, that the new formulation helps to reduce the proportion of patients with stomach irritation? That's what the manufacturer hopes, compared to the current pain reliever. The conditions for inference have been checked and verified. That also seems important since we're going to have to do an inference procedure. We are always happy when the question tells us to assume that the conditions for inference have already been met. You remember the first piece of advice? Start with what you know. Well, this is an inference problem where we're being asked to do some kind of test. And as you recall from a previous session, what's required on a significance test are these 4 steps: stating your hypotheses, identifying procedure and checking conditions, but we know they're already checked and verified, performing our calculations of the test statistic and the p-value, and finally making a conclusion in context. So if we just start with what we know, we should be able to get through part A in fairly fine form. So let's start step by step. We'll state our hypotheses. The null hypothesis is P current minus P new equals 0, or that P current equals P new, that they're the same proportions. And the alternative is that P current minus P new is greater than 0. So we will explain that. The current pain reliever is the one that we think will have a higher proportion of stomach irritation than the new formulation that's supposed to be easier on the stomach. So P current would be greater than P new in that case. Now we need to define our parameters here. We can't just throw the symbols around. So P current is the proportion of patients who would suffer stomach irritation if treated with the current pain medication, who would suffer hypothetically, not who did suffer, because that would be referring to the sample proportion. We don't refer to the sample proportion in our hypotheses. It's about something larger than the sample. And P new is the proportion of patients who would suffer stomach irritation if treated with the new pain medication. So we've stated our hypotheses and defined our parameters. We're using a 10% level of significance, so we'll keep that in mind. On to step 2. Identify the procedure. We need to do that. Check the conditions. We don't need to do that, thankfully. So we'll go to the inference flow chart, one of our vital resources. We start by identifying the individual or case. Well, it's a patient who is suffering in this case. A variable of interest in this case is stomach irritation status, I'm calling it. Type of data, well, they either have stomach irritation or they don't. So that's a categorical variable, stomach irritation status. So we're doing inference about categorical data. And because it's a one-sided alternative hypothesis, it can't be a chi-square kind of procedure. Just want to point out that anytime you have a one-sided alternative hypothesis, you have to be doing inference about categorical data for proportions. So let's go to the flow chart. We've made it to the first stage, inference about categorical data for proportions, but we need to move on through the flow chart. Do we have one sample or two samples? Well, we have two groups in a randomized experiment, so we have two samples. And then are we being asked to estimate a difference between the two parameters, or are we being asked to test a claim? We're being asked to test a claim. We stated our hypotheses, so we'll do a test, and the correct test is a two-sample z-test for a difference between proportions. So we've identified the name of the procedure, two-sample z-test for a difference between two proportions. Notice on the previous slide, I did it symbolically. That would work here also if you used p current and p new like we did on the previous slide. Now you should know what the conditions are just in case you're asked to check them. We need to be sure we've got independent observations, and we also need to be sure that the sampling distribution of the statistic, in this case, the difference in the sample proportions, is approximately normal. So if we were asked to check the conditions, we'd need random assignment, and we would need to be sure that the expected counts of successes and failures in each group would be at least 10. Just wanted to remind you of those in case it should come up in the future. But the conditions for inference have been checked and verified, so we don't have to do that. And in fact, we don't want to do that. Why? It wastes time, and you might do it incorrectly, and then the grader would have to penalize your response because you've done incorrect statistical work. So let's move on to the things we have to do. Step 3 is to perform the calculations. We need a test statistic, and we need a p-value. You might remember in session 5, I discussed two options for doing the calculations on an inference procedure. One was to use the formula sheet. So let's remind ourselves about that. We're doing inference, so we're not in the section of the formula sheet 1 or 2. Those are about descriptive statistics and probability and random variables. We're down here in section 3 and beyond, sampling distributions and inferential statistics. We're going to need a standardized test statistic. And then on the back page of the formulas, we're going to need something for two population proportions. And we're in this special case where it's assumed that the two true parameters are equal, where there's no difference between them. So we're going to have to use this special formula to get the standard error in the denominator of our test statistic. And we're going to have to compute this p hat sub c, the combined or pooled proportion of successes in the two samples combined. And that's a reminder, whether you're checking the conditions or you're performing calculations for a test of null hypothesis of no difference in the true proportions, you should use this p hat c for the calculations. It tells you on the formula sheet, and it's something that you should remind yourself about. All right, well, here's a quick summary of the different proportions going on. We've got the sample proportion who developed stomach irritation in the current pain reliever group, and the sample proportion that developed stomach irritation in the new formulation group. And you can see the one for the current group is higher. So there is some evidence that the new formulation is reducing stomach irritation. And this combined proportion, we just add the two numbers of quote unquote successes having stomach irritation and the two sample sizes together to get an overall proportion of 38% of all the patients in the study who experience some kind of stomach irritation. We're going to assume that is the correct value for both p current and p new, the true parameters for now, because we're assuming they're equal. And if we're assuming they're equal, we need something that they're equal to. So we'll use that number in our formula for the standardized test statistic, which is a z statistic for comparing two proportions. It's the difference in the sample proportions minus the hypothesized value from the null hypothesis divided by the standard error. We've got the difference in the sample proportions here of 0.08 minus 0, and then we plug in the sample results down in the denominator there. We get a p-value of 0.2061. And how do we get that? We get it from the tables, right? So we look up our z statistic that we got in our calculation, the z statistic of 0.82, and we scroll down until we find 0.82 on our chart. and it looks like 0.7939, so about 0.20, somewhere around there, 0.2061, if I did my subtraction correctly. Yep, 0.2061. Now, I think we talked about this in session 5. That's a lot of work. I mean, this is just part A. So another option that might be more efficient is to use the calculator. Here is the output from a 2-proportion z-test on the TI-84 or TI-83. And you can see the z-statistic is very similar up to rounding to what we got from the formula sheet, and the p-value is about 0.2049. Similar, but not exactly the same due to rounding when we were calculating with the formula. So we have what we need here. We have the test statistic and p-value. We would just write those two numbers down on our paper, and we would be done with step 3. Finally, we would need to make a conclusion in context. So it says, since the p-value of 0.2049 is greater than the significance level of alpha equals 0.10, the null hypothesis is not rejected. There is not sufficient evidence to conclude that the proportion who would suffer stomach irritation is less for patients treated with the new pain medication than for patients treated with the current pain medication. The p-value is fairly high. It's certainly above our 10% significance level. Therefore, we fail to reject the null hypothesis. And you might have noticed something that I've done in a couple of videos is to use the wording in the stem to help me guide the formulation of my answer. That's also a good strategy. I don't know if you remember, but this is just part A. So if you complete part A successfully, you will have earned credit on the investigative task, but you might make a little bobble here or there. So we need to keep going, trying to earn as much credit as we can. In part B, it says, based on your conclusion in part A, which type of error, type 1 or type 2, is possible? Describe the consequences of each error in the context of this study. So which type of error and consequences of each error. That would be easy to miss in the reading if you don't read very carefully and actively highlight or underline or circle something in the phrasing. So let's take a look at the first part. We failed to reject the null hypothesis in the previous part. So that means if you fail to, the only type of error you can make is a type 2. Fail to goes with type 2. For your memory reminder. So it's possible we committed a type 2 error, which is the failure to reject a false null hypothesis. What would be a potential consequence of that? It would be that the marketing of this drug is going to be delayed because you don't really believe it reduces stomach irritation. And that is preventing more people from receiving this medication who could be helped with this new medication for pain relief and in fact experience less stomach irritation. But because the study didn't give convincing evidence of that, if it were the case that the new drug was less harmful on the stomach, we wouldn't know that at this point. But we have to describe the consequences of a type 1 error, even though we could not have made such an error. So a type 1 error occurs when you reject the null hypothesis, but the null hypothesis was actually true. So that would mean marketing and promoting the new drug over the current drug, when in fact the new drug is not less likely to cause stomach irritation than the current market drug. That would be unfortunate also, but that's not a type of error we could have made in part A because we failed to reject the null hypothesis. So this is quite intensive. You've done these things before, describing a type 1 error or a type 2 error. You've described consequences, I'm sure, in your course, but this is asking you to do several things just to earn credit for part B. We should be on the lookout for an unexpected twist because so far parts A and B have seemed pretty familiar. And here it comes. After the preliminary study, one of the researchers of the company suggested that the procedure described above would have more statistical power if the sample size was increased and recommended that a simulation study be conducted to investigate that more completely. For the purposes of the simulation, the researcher assumed that 40% of the patients on the current pain reliever will have stomach irritation, and then only 30% of the patients on the new formulation will have stomach irritation. Further, the total sample size will now be 200, with 100 subjects randomly assigned to each treatment. So as a recap, they're assuming that the true proportion of patients who would suffer stomach irritation with the current pain reliever is 0.4. For the new pain reliever, new formulation is 0.3, and that both group sizes have been enlarged to 100. So we have some specific values that the researchers are assuming. So the 10 percentage point difference in the effectiveness of the two drugs on stomach irritation, or the reduction in stomach irritation based on the new formulation of 10 percentage points, is what we're assuming. It says 100 trials of a simulation were conducted, and a p-value was calculated for each trial based on the testing procedure, significance level, and hypotheses used in Part A. A histogram of the p-values is given below. Use the information in the histogram to estimate the power of the test if the test is performed at the 0.10 level of significance. Indicate how you obtained your estimate. So we can't just give an estimate with no explanation. It's very important that we show our thinking. This is a little outside the box, but you should know what the power of a test is from your course. It's the probability that the test will correctly reject the null hypothesis when a specific alternative parameter value is true. In this case, the alternative parameter value is 0.1. The difference in the two parameters is really 0.1, and the simulation is done assuming that. Okay, so what do we need to do to figure out if we're going to have power for our test? We need to figure out if the test is going to reject the null hypothesis. When will the test reject the null hypothesis? At the 0.10 level of significance, if the p-value is less than 0.1. So on the graph, we need to look and see where the p-value is going to be less than 0.1. And of course, that's over here on the low end of the graph. And then we just need to kind of count up how many of the trials out of 100 that happened for. So I got 45 roughly for the first one and about 11 for the second one. So I'm getting 56 out of 100, or about 0.56. So the power of the test to detect that 10 percentage point difference, if in fact that's the case, with sample sizes of 100 and 100 and a significance level of 0.1, is 56%. Now, that strategy I mentioned earlier, maybe this part just throws you. You've never seen anything quite like it, and you can't come up with an answer that you're very confident about. Put down some answer that's relatively sensible, like between 0 and 1 for the power of a test, or if you list it as a percentage, between 0 and 100%. And then you can use that answer as we go on to Part D. Part D says, explain in the context of this study what the value obtained in Part C represents. So we need that value from Part C. Remember those assumptions? I'll just keep putting them here so we can discuss those. And the estimated power we got was 0.56. But if you had to make up an answer, you would just use your value. So with all this information, we're ready to summarize. As I mentioned, a common endpoint to these problems is some kind of summary. On the previous one, it was trying to think about all the different graphs you had done and summarizing how you could have a confounding variable actually describing the relationship in the baseball setting. Here, we're thinking about what we did in Part C and how it connects back to the earlier parts of the question. So a possible answer would be the value of 0.56 is an estimate of the probability of rejecting the null hypothesis, which assumes the proportions of patients who would experience stomach irritation are the same for the two medications, when actually 40% of the patients taking the current medication have stomach irritation, and 30% of the patients taking the new medication will have stomach irritation. And the sample size is 200, and a significance level of 0.10 is used. All those inputs are part of describing the power of the test. In repeated random assignment, we would expect about 56% of the time to make a correct decision to reject the null hypothesis under these circumstances. So that last part is, what does that probability represents? It's the probability that if we were to repeat the random assignment, about 56% of the time, we would correctly find convincing evidence for the alternative hypothesis, which says that the new formulation helps reduce stomach irritation, because in fact, it reduces it by 10 percentage points under the assumptions here. Wow, you've seen two pretty substantial 4-part investigative tasks. But be honest, you can do one or more parts of these questions based on what you've practiced to this point. It's just that it's a really long and intricate question that kind of takes a winding path, and you have to be prepared for that in order to truly be successful. So what should you take away from this discussion about investigative tasks and how to tackle them? Well, let's recap the essential content and skills that we addressed. First, of course, is comparing distributions of quantitative data. In an earlier session, we described a distribution of quantitative data. You definitely need to be prepared to use that skill on the exam. Describing relationships between variables in scatter plots. And what made it interesting was we threw in a third variable that had to do with old or new stadium, and that complicated the discussion. And then to summarize, we had to identify and justify a potential confounding variable. That was certainly outside the box and quite challenging to do to meet the scoring guidelines. Then in the second question, we performed a significance test for comparing two proportions based on a randomized experiment. That was just part A. Then we described type 1 and type 2 errors and their consequences. And in the last parts, we estimated and then interpreted the power of a test based on a simulation. We did a lot of content in just 2 questions, and that's because these are investigative tasks. They cover content from multiple units, and they require you to synthesize them in ways that you haven't done before. Let's talk strategy. There were 5 specific strategies that we discussed before and during the session, starting with what you know. One or more parts of the question will be in your wheelhouse. Take advantage of those parts to earn as much credit as you can before you get to those other parts. And then speaking of those other parts, be prepared for that unexpected twist. You know it's coming. This is an outside the box question that's requiring you to transfer your understanding out into a different arena. So just be prepared for it and don't get intimidated by it. If you get stuck on a part, make up an answer. We showed an example with a numerical answer for estimating the p-value. Be ready to summarize. It's likely to happen somewhere within the question, possibly right at the end. And finally, don't forget, manage your time wisely. You've seen now how long it takes to do one of these questions, start to finish. One part can be as big as an entire one of the previous 5 questions. So you have to manage time wisely during the exam and while you're working on this question. And I hope that what we've done in this session has really helped build your confidence about the investigative task and will help you maximize your exam score by ensuring you don't get a 0 on the investigative task, and then in fact you follow these strategies to earn as many points as possible. I want to thank you for tuning in. I'm going to encourage you to join us for the last session, where Luke Wilcox and I will be giving our top 10 strategies or tips for helping you get ready for the AP exam. If you feel like you need some additional support relating to investigative tasks, feel free to go back and take a look at earlier AP Daily videos, as well as to look on AP Central for those question 6s from previous released exams. Again, thank you for tuning in. Really hope to see you for session 8. Bye.